Hello guys, in this video we wanna implement LinkedList, and let's see what we wanna do. There's a whole bunch of methods that we wanna implement, so this must be a pretty long video, I think. So let's start. But firstly, let's try to I'll show you how LinkedList works. With some visualizations. So as you can see, LinkedList is a data structure where each node, this one, as you can see, is a data structure where nodes are connected with each other. One node has data part and a pointer. The pointer will point to the next node. Pointer of node A point to node B, pointer of node B point to node C, and so on. The last node pointer points to node, and we also keep track of the head node. As you can see, there's a pointer that points to the first node of the linked list. So that's pretty much it. Let's see what we're gonna implement. The class instance represents node have two properties, data and next. It's exactly what I've explained, except both these elements to node constructor and assign them to instance properties, data and next. If next is not provided to the constructor, then default value is no. It's pretty straightforward. Let's see, we have node class. I'm gonna write a constructor with data and next. And if next is not provided, it should be no. By default, we assign argument to the property of node class. This is next equal to next, right? So after doing this, you can see there's one more test pass, and our goal is to make all the tests pass, right? The second thing we want to do here is constructor create LinkedList with no head. When first created, LinkedList with no head. So the LinkedList instance will have one property, head, which is a reference to the first node of LinkedList. By default, head should be no, right? We a constructor for LinkedList has one property, head, that point to know when the LinkedList is first created. Let's start with insert first. Create a new node from argument data and assign the result. Not head property. Make sure to handle case in which the LinkedList already has a node assigned to head property. So insert first, right? So first text in data. Let's create a new node using the data. Let's new node equal to new node data. It creates a new instance of node, and there's two cases we may have to handle here, which is the first case is the linked list is empty, so probably the head. Let's try to visualize if the was empty, then the head pointer will point a node, right? So we need to insert a new node, right? New node. So it's simply by pointing the head to the new node, right? This dot head equal to new node. But if the case, what if the case when the linked list is there's elements in the linked list? For example, 1, 2, 3, I don't know. Right. Initially, the head pointer 1, right? So only move the pointer to the new node is not enough. We need to make a connection from new node to the old head, right? So how to do that? So new node will go to at this point head is still point to 1, right? So we simply point next of the new node to the current head, right? Current head, which is 1, and right. But you may wonder if this new line of code will break. Will not work for the first guy we've discussed, which is the linked list is empty before. It is still work. Actually, as you can see, we create new node, right? And this line we've just added, we point new node to the current head, which is null. So it definitely will work for both cases with these 3 lines of code. And we point head to new node, head point to new node. So let's run a test. Hopefully we have 4 paths. Okay. For the size, return the number of nodes in the linked list. Size function return a number of nodes simply by let's say 1, 2, let's say A, B. So this link list should return 3, right? Expect return 3. So the only way to solve this kind of problem is try to traverse the linked list from head to tail. Right, we keep a count variable start with 0. So as long as the current value is not null, we increase count by 1. Right? We move like B is not null, increase by 1. C is not null, increase by 1. Right, so but as we go to the next node, it's null, so we stop the loop, right? But what if the linked list is empty? Then imagine that the head will point to null for that case, so it will not run into the loop and the count will still 0. So let's implement it. We initialize count variable equal to 0. So as long as we may need a pointer, a working pointer. Let's name it current point to this dot head. So as long as current is not null, as long as we has a current is a node, then we want to increase the count by 1 and move to the next node. And after we exit the loop, which means the current is null, so return count, right? Hopefully we have 5 pass. Awesome. Get first. Return the first node of the linked list. Return the first node of the linked list. It's pretty easy one, I think. Simply return the head node. This not head. Sig pass, right? Awesome. Get last. Return the last node of the linked list. Return the last node of the linked list. For example, 1.2.3. We have the head pointer 1. So we expect it will return the node with value 3. So how we can solve it? So our goal here is to go to the node that is next node is no, right? Our goal is to go to the node that its next node is no. So it means as long as there is next node, but let's initialize a working pointer that initially point to the first node, pointer current, pointer is at head. So as long as we have next node, current node next, right? As long as we have next node, then we want to move the pointer to the next node, right? So that current next node, current will point to current next. So we are here, we are 1. Is there the next node? Yes, it's node with value 2, right? Move the pointer forward. Is there next node now? Yeah, there is. Move the pointer forward. Is there next node now? No, we stop here and return 3, right? So after we exit the loop, it means that there's no current next, right? Or in other words, current next is no. It means we're already at the last node. Just simply return current, right? But there's one more case, which is what if the head is what if the LinkedList is empty? In that case, current will be no, right? And if we accept next property of no, it causes no pointer exceptions for sure. So in order to avoid that problem, we might check if only we have current. We have check current before we check current next. So if the current is no, we simply skip the while loop and return no, right? So that's it. Hopefully it returns 7 pass. Awesome. Get last already clear. Empty the linked list of any nodes. Actually, the linked list is determined by, is identified by the head node. No, not the head node, but the head pointer. Every operation should start from head pointer. So simply by, if we want to clear the linked list, simply by pointer head node to node. This head go to node. Hopefully return 8. Nice. Awesome. Yeah, we move first. How many cases? What if so we only want to remove first if there's at least one node in the linked list, right? So if the head is null, the linked list is empty, which has a node is not head, just return. But if it comes down here, it means there's at least one node in the linked list. So 1.2 point, for example, but the point over point 2.1, we want to delete the one is simply by point the head node to the next node, okay? But what if there's no next node? What if this one is no? Then it means we will point the next node to no, so it still work. Let's try it. Remove first simply by point head to the this dot head dot next. Okay. We point this to this one, and to have access to this one, we use this dot head here and point next. Use the next pointer to get this one. So hopefully we get 9 passing tests. Awesome, we have 10 passing tests. Remove last. It's 22 minutes already. Remove last. Remove the last node of the change. The same here. We don't want to remove last if there's nothing in the head if the linked list is empty. So let's say 1.2 point no. Initially pointer 1. Okay. In order to remove last, is simply by we must reach the node previous the previous node of the last, right? If this one is last, then we must come to here and point and change the pointer of this node to null. So removing is simply by pointing the next to null. But what if there's only one node? What if there's only one node? It means if there's only one node, then we can't get to the previous. I said earlier, we must come to the node before the last node. If there's only one node, we cannot go to the previous node of the last node. So try to think for a second. Think about it for a second. We've already implemented remove first here, so if there's only one node in the linked list, it means we need to remove the first node, right? So if this dot next this dot has, if not this dot head but next, right? Here we go. Here it means we have this dot head, but if we the head the node the head node is point to null, which we don't have the next here, so it means we will remove first, and this function will handle that. Return, remove first and we return. But if we come down here, it means let's if you come down here, it means we have at least let's say we have at least 2 nodes. We have at least 2 nodes in the, let's say we have 3 nodes. Initially, the head pointer initially the head will point to 1, and our goal is to come to this node, because this is a node that comes right after the last node, which is 3. So we want to stop here. We want to stop traversing here and pointing this to null, so that we remove this one from the linked list, this part from the linked list. So now to check how to stop this one. So we want to stop when the next and next of next, right? We want to stop when the next node of next node is in other words, the next node of the next node is null, right? So it means that the stopping conditions, if we don't have the next node of the next node, then stop. It means as long as we have the next node, let's initialize the working pointer, which is current is not have. It means if we have current.next and current.next, then we want to we don't need to check the current. We don't need to check if the current is not empty, is not null here, because by doing this, it already checked for that condition. So if we have current dot next, and so here, for example, we are sitting at 1. Do we have next? Yes, we have. We'll have next of next. Yeah, we have next of next, right? So current of next. We point to the next. Again, we run this one to move the pointer forward. Then check again. Do we have next? Yes, we have 3. Do we have next of next? No, we don't. So we exit the loop as long as the condition is not met. We exit the loop. So the pointer is the working pointer is pointing to the node before the last. So simply by pointing it to no. So yeah. Let's see if we have more tests, passing tests. Awesome. Remove last. Insert last. Insert last. Let's see. Insert a new node to with provided data at the end of the change. We remove last. Now we insert last. How to insert to the last? Let's say let's create the new node first. Insert last, which means we must go to the last, right? Then change the point of the last to the new node. So you see that we have the get last function here. We can use it. Get last, maybe no as well. So we need to take that into account. Last node equal to this dot get last. Nope. Get last. We can do last node, but if we don't have last node, it means if not last node, it means the linked list is empty. Then the linked list is empty. It means we just point ahead to a new node. Otherwise, else, if we have last nodes, then we point last node to new node. Hopefully we'll have more than 40%. Awesome. So let's check. First, insert last. Yeah, we have one test only. Let's move on to the next method. Get at. We have 3, 5 more. Get at index. Right. Return the node at the provided index. So it 0 base index, right? As you can see, if we get at index 1, let's return B, right? So let's say if A, B, C, no index, the pointer initially point to head. So how about, what if index is 2? We want to return B, right? Let's assume that index is within the range here. Get at. What if index 1? So about count down the index until it reaches 0. So it means it comes to the right one. Right? So for example, it's 1 here. Here the index is 1, and we want to stop when the index is 0. Okay. Want to come here. Here is the index 0, index 1. So there's two ways, which is the first way, use a counter variable to count upward from 0 to the index, but more clean way is to just count out the index variable till it reaches 0. Index 1. So we check, is the index still greater than 0? Yes. Okay. We decrease the index by 1 and move the pointer upward. We check again, is the index still greater than 0? No, 0. So we are sitting at the node we want, which should be a little bit tired. Let's say we need a pointer head first, a working pointer with a head first. So as long as the index is greater than 0, we want to move the pointer forward current equal to current.x. One thing we can do here is to save checking, because here we accept next property of current and want to make sure that we don't accept if the current is null. So only if index is greater than 0 and we have current, then we move to next, right? So after we exit the loop, it means the index is 0 or will not have the current. The current is null. So if the index is greater than if the index is 0, it means we're already at the node we want. We just return current. But if it is the case that we exit the loop when we don't have the current, which means in that case we return current, means we return null. So yeah, it will work. 15 tests. Let's see. Get at. Comment it down. We still have 15 tests, so probably it's good. Let's see why it work. Oh, I know why. Because if the index if the index is out of range 0, 1, 2, 3, cannot read. Probably data no. What is wrong here? Current working pointer by the head. That's all. We forgot to decrease the we go. Seeking passing test, right? Awesome. Remove at index. In order to remove an index, say A, B, C. No. What if index is 1? It means to remove at this one. The same for removing operations. We need to go to the node before the one we want to remove, then point that node to the next up next, right, which is C. So by doing that, we are removing B, right? So you can take advantage of this one to help us to find the previous node at the index. So let's find the conf node equal to get it index -1, right? But what if we're removing the first node, the head node? Then we cannot find the previous node. So how about check the if index is equal to 0, which means we for the first node, right? We already implemented it. So return. We remove the first and return. If we come down, it means index is greater than 0. We're not removing the first one, so we can find the previous node of the deleted of the node to delete. But what if the index is out of range? How we can handle this? So probably, if that's the case, we want to but firstly to handle the normal case first. Previous node. What if we go to previous node? Okay, previous node. We point previous node to here. We have previous nodes. To not to delete. We point previous. We point the next pointer, this node, to this node, which is previous node. Dot next. Let's see. 16 tests, passing tests. With 19 passing tests. But it seems like we only passed the 3 tests. But delete not given index. Work on last node. Not work on last node. what if the index is out of bound? And what if the index is last node? If the index is last node, it still works fine. It still works fine because because the previous node will point to previous node will point to here. Previous node next is a deleted node, and that next is a null. If the deleted node is the last node, so it's still. But what if the index is out of bound? For example, 40. If that's the case, as we can see, get at what if so for the index greater than 0, but we exist this root because the current is null, and the current, so return current to null. So if the previous node is null, means it's out of bound. Wait, we need to check. What if the current in the case that index is outbound, it simply we do nothing for the case. So we only want to reassign the pointer if we had previous with 20 tests now. We're passing test. Remove and then crash on index now. Not index up no. So the previous may not know. The previous may not know, but the deleted node may be out of bound. So also for that case, we don't want to do anything, right? Brief. 21 passing tests. Let's move to insert at index. Insert at. Let's say if we want to insert it index 1, which is B, right? Let's say the node we want to insert is X. Then we must come to the node. If we insert X at index 1, it means it will be put between A and B, right? So that everything is pushed to the right. and now A will point to X, and X is point to B, right? So we have to somehow get access to A so that we can change the pointer from B to X, and to do so we need to get access to the node at index minus 1, right? Not index, but index minus 1. So const pref node equal to this dot get at index minus 1. But what if index is 0? What if we want to insert 0? Then this will not work. So if index is 0, we want to save checking, return, and just simply insert first, right? If we insert index 0, it means insert first. But if we come down here, so same logic here, we want to check only if we have pref node, and pref node is we have only the pref node, the previous node of the node to delete, and the node to delete itself. Only we have two of these, and if two of these are not null, then we want to really delete this node. In order to delete this node, change the pointer previous node. We point the next to the previous node, next, and the next, right? So hopefully it will work. 21 passing tests. Oh, sorry. No. It is deleting logic. Same here. What we want to do is to point this to the new node, right? This should be the new node. But the new node also need to point to the, as you can see here, if X is put here, X will have to point to B, right? So we want to do it over here. Const new node, and to point X to this part, we want to simply provide the next pointer for the constructor, which is previous node is A, and previous dot next, previous node dot next. So new node is now point to B, and now we fix the previous node A, point next, point to new node. Hopefully, it still not work. Oh, previous node next, to be exact. Oh, what's wrong here? new node. Return here if only when it can previous like create new node with data and the pointer point to what previous node is pointing now. Then we fix the next pointer previous node to new node. It should work. Insert add. We forgot very important thing, which is the data itself. Insert add. The first argument is data. 22 tests. Middle index. But when the list is empty, simply do nothing. When the list is empty, insert a new node at 0 index. When the list is empty, okay. When the index is 0, or index empty means there's no head. Pass data here. 24 tests. Insert a new node with data at the last index. What's wrong here? New node with data. Last index means it's 2 here, right? Go here, previous node and previous dot next. Okay. It should work. Insert a new node with data at last index here. We go to B, right? Breath node is not to B. Breath node next C. Delete node. With new node with data. Let's point to point to C. X point to C. Then we want to point B to X. Remove this connection. Point to X. It should. What's going on here? So the last index, let's see. Data set A, B, insert the last. Right? I got it. Oh, so last index. Not here, but it is insert as is here, and it's a case that if we don't have previous, else if previous dot neck is previous dot next, but don't have previous next. But they know in the case we want to insert last, right? Return this dot insert last data. Still to define this. Insert a new node when index is out of bound. If the index is out of bound, we always insert the last, right? So it means not go to this if should always insert the last. Correct. Awesome. Let's try to implement two last method. For each call the provided function with every node and change. So for each we take in a callback function. We want to run it for every. When we run a callback and passing in every node. So definitely want to check out the node. We need working point which current pointer does not have first. So as long as we have current, as long as current is not no easy node, then we want to we want to run the callback passing in the current. Say we want to provide an index, also pass in the index, and after that increase the index by 1. Then we want to move the current working pointer upward. Okay. So as long as gun is not null, if the gun is null, we exit the loop. We don't want to pass null to callback, right? So let's run it. Hopefully we have 7 passing tests. Awesome. For off loop, this little bit JavaScript oriented example. So actually you may want to Google it a little bit you need to do a little bit of Google to know the syntax. What's simply a way to it is simply a way to loop for every node in for of syntax. Right? If you want to do for syntax for a custom object, we need to do something like this. So a little bit to right iterator we set the current head, right? As long as we have current, I'm gonna go inside, we want to yield the value current. I will not explain about it right here, all the mysterious syntax. Yes, you might want to do it yourself, a little bit Googling, you figure it out by yourself. Yeah, and yeah, what the point of all. Hopefully awesome. It's pretty long video already, so if you manage to still watching right now, and thank you for watching the video.